In the previous few videos, we've talked a lot about limits. We've looked at them geometrically and kind of learned about one-sided limits. We looked at them a little bit algebraically, but really I just tried to impress upon you this idea, this big picture thought about what a limit represents. Sort of what the output of the function gets really close to when the input gets really close to some number. And hopefully that's all making sense, but the more impatient among you might be like, okay, but what does this have to do with what I learned in the previous sections? What's average rate of change have to do with any of this? I feel like I'm learning a lot of completely disjointed topics. How do they all tie together? Well, the short answer is they're really going to tie together in the next section. But in this specific video, I can start to show you some examples that might look somewhat familiar. So in this video, we're just going to go over these three examples right here. They're just limits. They don't say anything about average rate of change or anything else. But I think when we end up solving these, they may look a little bit more familiar than maybe you think. What's the limit as x approaches 3 of this function right here? X squared minus x minus 6 divided by x squared minus 3x. There's a few different ways we can figure out this limit. There's kind of an inefficient way that we've learned in previous videos that we're not going to do in this video. We could call this thing, I don't know, f of x maybe. And then we could just evaluate this function at points really close to 3. So, I don't know, f of 2.9 maybe. And then f of maybe 2.99. And then maybe we'll want to look at kind of the other side of 3. So 3.1. And then maybe 3.01. And maybe when we evaluate all these numbers, we can look at them and get a pretty good guess of what this function appears to approach when its x value approaches 3. That's our first option, and that'll totally work, but that's not what we're going to do. A second option that you might want to try is just to evaluate f of 3. Hope that this function is continuous when x equals 3, in which case we can use what we learned 2 videos ago and exploit the continuity of the function at that point to evaluate the limit really simply. Unfortunately, that's not a good option either. In the red option, we'd end up kind of guessing at the answer, and it'd be really tedious. In the green option, when we try putting 3 into this function, we're going to get an undefined output. So it doesn't work at all. I mean, try it out. 3 squared is 9, minus 3 is 6, minus 6 more is 0. 3 squared is 9, minus 3 times 3, which is also 9, leaves me with 0 on the bottom. When I put 3 into this machine, 0 comes out on the top and 0 comes out on the bottom, and 0 divided by 0 is undefined. I get no information about this limit. You're like, okay, so how about you stop telling me what I should not do, and maybe show me what I should do? Option 3. And option 3 is going to be the best way to approach limits going forward, and it's going to be the way we solve all of the problems here. It's the most powerful method of evaluating limits, and it involves algebra. The idea behind option 3 is when you have a removable discontinuity, when your discontinuity is an open circle, a hole here, and you want to evaluate the limit at that point, all you have to do is, loosely speaking, get rid of the hole. Remember the first 2 graphs we looked at, g of x and f of x, in the very first video in this section? They were almost the same. They were identical except for this open circle. What we're going to learn in this video is how to take graphs like g of x and fill in the open circle to turn them into graphs like f of x. Why do we want to change g of x into f of x? Because f of x is continuous. So we can take advantage of the continuity at this point 5 to evaluate the limit by just putting 5 into the function. If we can learn how to change graphs like g of x, functions like this one right here, into graphs like f of x, functions like this one right here, we can exploit continuity and evaluate limits really easy without ever looking at points on the left and points on the right of the given x value. You're like, all right, cool. How do I do that? Well, it stems back to something that you may have learned about holes in a pre-calculus class when you were studying rational functions. The idea is you will have a hole at 5 if and only if there's a factor of x minus 5 in the numerator and a factor of x minus 5 in the denominator of your function. That's the only way for graphs like this to exist, is if you have a function and in the numerator it's something times x minus 5 and in the denominator it's something times x minus 5. You're like, I don't really remember that. Is that what happened in this one right here? It is, you just can't see it, right? In the denominator it's x minus 5 times 1, and in the numerator it's something times x minus 5. It's just written in a way that that's hidden. In case you're curious, where I came up with this polynomial is I took x minus 5 and I multiplied it by x squared minus 3x minus 2. The way I created this graph that looks just like x squared minus 3x minus 2, except it has this open circle here at 5, is I took x squared minus 3x minus 2, and I multiplied it by x minus 5, and then I divided by x minus 5, creating that hole at 5. And now that you know how these holes are created, we can learn how to get rid of these holes. If you were able to change this function g of x into this form, you could just cancel these guys out, and by canceling out these x minus 5s, essentially you're filling in this open circle, changing this graph g of x into this graph f of x, which is the one that's so easy to evaluate, taking advantage of continuity. If this isn't here and this isn't here, there's no problem changing all the x's into 5s here. That's a lot of theoretical stuff. Let me take you through some actual examples. Let's evaluate the limit as x approaches 3 of x squared minus x minus 6 divided by x squared minus 3x. If we factor the numerator here, we can rewrite x squared minus x minus 6 as x minus 3 times x plus 2. This is a quadratic trinomial with the leading coefficient of 1. So all we're looking at for are two numbers that multiply to negative 6 and add to negative 1. Those numbers are negative 3 and positive 2 respectively. And if we look at the bottom, you might notice that each of these two terms have an x in them, so we can factor out that x, and what we'd be left with is x minus 3. Note that when we factor the numerator and the denominator, we've ended up with this common factor of x minus 3. Because there's a hole at 3, we can't evaluate this limit by just changing all the x's into 3's, right? We saw that before. Try evaluating f of 3, you get an undefined output. But what we could do is cancel out these x minus 3's. And this is kind of a subtle step. I don't know how much of this you really need to know, but I'm going to say it anyways. When we cancel out these x minus 3's, we get x plus 2 divided by x. And you're like, oh, x minus 3 times x plus 2 divided by x times x minus 3 is the same as x plus 2 over x? No, it's not. This is not the same as this. You can't cancel out these x minus 3's if these are just expressions. But the fact that I'm writing the word limit out in front here allow me to cancel out these x minus 3's. So really, it's not that this is equal to this, because you can't cancel out variables from the numerator or the denominator, even though you've probably done that in a lot of math classes up to this point. Technically, to write this equal sign right here, I need to include this limit here. The limit as x approaches 3 of this is the exact same as the limit as x approaches 3 of this. The bad news about this limit is it's hard to evaluate. I can't just plug in 3 everywhere. The good news about this limit is it's easy to evaluate. You can just change all the x's into 3's. 3 plus 2 divided by 3 is just 5/3. The limit as x approaches 3 of x plus 2 divided by x is 5/3 because x plus 2 divided by x is continuous at x equals 3. So evaluating the limit is as simple as plugging in x equals 3. What made this hard is I couldn't plug in x equals 3 from the start because this function has a hole at 3, which we see when we factor the numerator and the denominator. That's the hardest thing we're doing in this section, but that's also the most important thing we're doing in this section. So I want to give you two more examples getting practice doing exactly that. Let's evaluate the limit as x approaches 0 of this mess right here. Bad news. If we consider this expression as a function, that function has a hole at x equals 0. Don't believe me? Try plugging in x equals 0 if you want. We'd be dividing by 0, and up in the numerator we'd have 8 divided by negative 4, which is negative 2. And negative 2 plus 2 is 0. Try plugging in x equals 0 and you get an undefined output. The reason why is because there's a removable discontinuity at the point where x equals 0. There's a hole. And guess what? There's always going to be a hole. Going forward, the type of limit we're interested in are this type with a removable discontinuity where we have a hole. So these aren't special cases. These are the cases that we're going to care about. So how do I get rid of that hole? Well, there's a hole at x equals 0 if there's a common factor of x minus 0, or x, in the numerator and the denominator. So what I have to do is cancel out this x with an x up on the top. How do I do that? Well, I need to algebraically manipulate the top so that it's x times something. It's a little bit hard to do when you have these fractions inside fractions. In fact, we saw that in the last section when we had rational functions. There's actually a really close connection between average rate of change with rational functions and this example right here, but it's okay if you don't see that right now. We'll get that in the next section. I got fractions inside fractions, so what I'd like to do is make this a fraction divided by a fraction. To make x on the bottom a fraction, that's easy, just put it over 1. And then I'm going to make this 2 a fraction by rewriting it as 2 divided by 1. The denominator's in good shape. It looks like a fraction. The numerator, I still have a little bit of work to do, but it won't be too bad. I have these 2 different fractions. I just got to add them up to make them a single fraction. Unfortunately, they don't right now have a common denominator, which is going to make life a little bit more challenging. But fortunately, I can make them have a common denominator if I multiply the top and the bottom of this fraction right here by x minus 4. First, make sure you do the top and the bottom, otherwise you're changing the value of this fraction. It's the same reason that, 1/3 is the same as 50 over 150. All I'm doing is multiplying the top and the bottom of that fraction 1/3 by 50. Same logic here, 2 over 1 is the same as 2 times x minus 4 divided by 1 times x minus 4 because I'm just multiplying the top and the bottom by x minus 4. So what does that give me? Well, I still have this 8 over x minus 4, but over here I got 2 times x minus 4, so I got 2x minus 8 if I distribute that 2. And then 1 times x minus 4 is just x minus 4. Things might appear kind of ugly, but they're actually getting closer to a form that we can deal with because now we have a common denominator. And you can add fractions if you have the same denominator. Think 1/5 plus 2/5 equals 3/5. You just add the numerators and collect the denominators. So 8 plus 2x minus 8 is just 2x. And then the x minus 4 and the x minus 4, I just write one time. Down in the bottom, I got x divided by 1. I've done a lot of work, but I'm one step away from that really satisfying canceling step. I got a fraction divided by fraction, and the way you divide fractions is just like multiplying fractions, but you multiply by the reciprocal of the denominator. In other words, take the fraction down on the bottom and flip it upside down. So instead of x over 1, it's 1 over x. This is equivalent to this, but this form is much preferable because we can cancel over multiplication. Because of this multiplication sign, we can cancel this x and this x. Note, you could not cancel this x and this x because of this subtraction sign. You can't cancel over addition and subtraction, but you can cancel over multiplication and division. This cancels with this. I'm going to get rid of the red just because it makes it hard to read. And I get the limit as x approaches 0 of 2 divided by x minus 4. Quick side note here, you can't really cancel out these x's because you can't cancel out variables, even though, again, I know you've been doing it your whole mathematical career. Technically, this expression is not the same as this expression. They're almost the same. The only difference is this one has a whole at x equals 0, whereas this one does not. So as long as I write the limit as x approaches 0, then I can put this equal sign in here. Anyways, this as a function is continuous at x equals 0, so to evaluate this limit is super easy. Just change all the x's into zeros. 2 divided by 0 minus 4, 2 divided by negative 4, negative 1/2. The limit as x approaches 0 of this is negative 1/2, and this limit is the same as this limit, so the limit as x approaches 0 here is just negative 1/2. That was a lot of algebra, but the good news is one of the types of these limits that you'll end up seeing will be the type that kind of has these fractions inside fractions. And when you're in the case where you have fractions inside fractions, you follow exactly this method, right? Where you turn everything into a fraction, you make it so it's a single fraction over a single fraction, and you multiply by the reciprocal of the denominator. If this feels familiar, it's exactly what we did with average rate of change when we had a rational function. We'll make that connection more clear in the next section, but before I get there, I got to do the last example in this video and the last example from this section. The limit as x approaches 10 of this mess. You might hope that this function's continuous at x equals 10, and you might hope to plug 10 in and figure out what comes out, but you'll quickly learn that they never are. Unless I specify that the function's continuous at 10, it's not going to be continuous at 10. In fact, it's going to have a whole at 10. Meaning that the top and the bottom contain a factor of x minus 10. It's just hidden, it's hard to see. The one up top's really easy to see, but the one on the bottom's not. In case you don't trust me, you can try plugging in 10. 10 minus 10 is 0, 10 minus 6 is 4, the square root of 4 is 2, and 2 minus 2 is 0. You try plugging in x equals 10 and you get 0 over 0, which is undefined, and that's precisely because I picked this expression to have a whole at 10, which is what makes this limit interesting. So how do you deal with this? Well, you got to cancel out this x minus 10 with the x minus 10 in the bottom. And you're like, I don't see the x minus 10 in the bottom. Yeah, me neither. But fortunately, there's a little trick that we can do. It's actually a trick that you've seen before. Although I wouldn't expect you to recognize it because it's a trick that was probably new to you in this class. The trick comes from multiplying by the conjugate. If you look at the denominator here, we have two different terms separated by this minus sign. We have a 2 and a square root of x minus 6. And one of those two terms has a square root sign here. In order to find the x minus 10 that's kind of hidden down here, what we need to do is get rid of this square root. The way we get rid of this square root is we multiply it by its conjugate, 2 plus the square root of x minus 6. You write the exact same two terms, the 2 and the square root of x minus 6, you just change the sign in between them. So from negative to positive, or if this were already positive, from positive to negative. And you're like, but wait, can you just multiply by stuff out of nowhere? Doesn't that change the value of this limit? Yes, absolutely. You can't just multiply the denominator by this. You have to multiply the numerator by the exact same thing. Oh no, this turned from something that was kind of ugly to something that's absolutely despicable. Like this is miserable to look at. But don't worry, it only gets better from here. Up in the numerator, I got x minus 10 times 2 plus the square root of x minus 6. It might be tempting to try to FOIL this out or something, but don't. Keep the x minus 10 separate because the x minus 10 is what we have to cancel out if we want to evaluate this limit as x approaches 10. The x minus 10 is what's causing the 0 over 0 thing. So leave this in its factored form. It's the denominator that you want to FOIL out because it's the denominator where you have to kind of find the hidden x minus 10. There's one there, you just don't see it. Don't trust me? FOIL. This 2 times this 2 gives me a 4. This 2 times this square root of x minus 6 gives me 2 times the square root of x minus 6. But this 2 times this negative square root of x minus 6 gives me negative 2 times the square root of x minus 6. So those cancel out. I'm going to write it, even though really you don't have to, because when you're multiplying by the conjugate, they're always going to cancel out. This O and this I in FOIL are the exact same, but one's positive, one's negative. Those cancel. What about the L in FOIL? It's the negative of the square root of x minus 6 times the positive of the square root of x minus 6. It's a negative times a positive, so it's negative. And it's the square root of something times the square root of that exact same thing. So I'm squaring the square root of x minus 6. Squaring a square root cancels out, and I'm left with just x minus 6. Be a little bit careful with the parentheses here. We want the negative of that entire thing. I claim this cleans up, and it doesn't look that much cleaner, but it really is. And we'll see that if we combine some like terms. Up on the top, I'm going to leave things alone. I got x minus 10 times 2 plus the square root of x minus 6. Down in the bottom, I got positive 2 square root of x minus 6 and negative 2 square root of x minus 6, so those two terms cancel out. I have negative x minus 6, which is the same as negative x plus 6 if I distribute this negative sign. There's the negative x, and the positive 6 can add to this positive 4 to give me a positive 10. We're so close, right? I want to cancel out this x minus 10 with an x minus 10 from the bottom. We're so close to an x minus 10 here. Oh man, I wish this said x minus 10. Well, it can with just one subtle change. Factor out a negative 1 from these two terms. Negative 1 times x minus 10 is the exact same as negative x plus 10, right? Take the negatives and distribute it through. When the signs of the two terms are the opposite of what you'd want, just factor out a negative 1 and that fixes everything. Now I got an x minus 10 and another x minus 10. I can cancel those out. Just like in the previous two examples, technically I got to be a little bit careful. You can't really cancel out these x minus 10s unless you're considering these limits, but because we're considering limits, you can. This limit is the same as the limit as x approaches 10 of 2 plus the square root of x minus 6 divided by negative 1. The good thing about this expression is it's continuous at x equals 10. Don't believe me? Try plugging in 10. I get 2 plus the square root of 10 minus 6 divided by negative 1. 10 minus 6 is 4. The square root of 4 is 2. 2 plus 2 is 4. I get 4 divided by negative 1. In other words, negative 4. The limit as x approaches 10 of this mess of an expression is negative 4. It's really challenging, but the good news is when we're simplifying limits in this class, they'll tend to be one of these three types. These polynomial types, these types where you have fractions inside fractions that are going to come from rational functions, and these types where you got square root signs floating around that are going to come from radical functions. And I think as long as you can follow examples A, B, and C, you'll be able to do all the simplification that you need for this section, which is the hardest part of this section, these algebraic simplifications to evaluate limits. It's worth pointing out that all of these limits you could evaluate this way using option 1, but don't. Eventually, you're going to have to do these the algebraic way, and if you just plug in numbers close to the given value, sometimes you can get misleading results. This works out totally fine if the limit is some nice whole number like -4. But when the limit is some really ugly fraction like -2/7, or if the limit is a square root that you don't know, like the square root of 3 or something, it won't help you to evaluate the limits this way. So for that reason, you're going to want to get in the habit of evaluating this way. In this specific homework assignment, I'll kind of tell you how to evaluate them, but I can just tell you going forward, the methods of this video that you just watched are the ones that will be the most important.